Hi everyone. In this talk, I'll discuss a mechanism that improves the responsiveness and resource efficiency of streaming systems for data analytics tasks. In this scenario, data analysts express these tasks as view maintenance over continually updating relations, represented by incoming data streams. The system is tasked with computing and maintaining the results for multiple concurrent queries as new data arrives. Analysts can also install new queries that are deployed alongside the existing ones, and these new queries may use some of the same streams that were already being subscribed by the existing queries. The system must provide initial results quickly to newly installed queries and update these results with low latency as soon as new data comes in. You can think of these as two dimensions of change. The relations are continually updated and the queries also change. This first dimension, handling continually arriving data, is well supported by traditional streaming systems, while the second dimension is generally well supported by data warehouses that can quickly provide results for new queries. This work attempts to support both dimensions. Multiple concurrent queries are deployed concurrently as new data comes in, and the analysts can interactively install and retire queries. These queries may contain both relational algebra operations and more complex iterative operators. As an example for this talk, here are two queries that perform joins on primary keys. In this example, the line items relation represents a set of facts that stream in continually, while we also receive updates for the dimension tables orders, customers, and suppliers. These join operators need to index at least one of their inputs and maintain these indices as new data comes in. In a traditional streaming system, each query is deployed as a separate and independent data flow, so each join operator needs to maintain the index in its private state. This of course results in unnecessary duplication of this index state, which must be generated and regenerated once per query. The core intuition for this work is to perform the indexing only once per incoming data stream, in what we call arrangements, and then share these arrangements among all the operators that need them. In this example, we index orders once, and then use the same index to perform the join with line items in both queries. Note that this scenario is different from multi-query optimization, as the selection predicates are often different across queries. Being able to share this index state means that we don't have to recompute it for each query. But now, of course, you need to worry about the concurrent access to these indices by multiple operators. The challenge then becomes balancing this opportunity for sharing with the fact that we will need to control access to these indices through additional coordination. Here, the key observation we make is that the pattern of sharing is single producer, multiple consumers. This is important because it requires less coordination than an all-to-all index you might find in a relational database, but it enables more sharing than the single producer, single consumer operator local state you find in a general-purpose streaming platform. So let's see how we support this single producer, multiple consumer access pattern while minimizing coordination. We do this by decoupling the write path from the read path to the index. On this slide is an arrangement, our single producer, multiple consumer index. An arrangement buffers incoming input tuples and uses the timestamps on these tuples to group them in batches. The arrangement takes this group of input tuples and indexes them as immutable batches. And because it's indexed, each batch supports efficient point lookups and scans. The arrangement then adds each newly created batch to a multi-version data structure. As new data comes in, index batches are constructed and added to the data structure. The operators that need access to this data can read the mutable batches through shared memory without the need for explicit coordination. Each consumer can maintain a separate placeholder in the multi-version data structure to keep track of which batches it has already processed. This way, each consumer is independent and doesn't need to coordinate with other consumers or with the write path. In this single producer, multiple consumer pattern, it's the immutability of the batches which makes it easy to share the index between multiple operators. We built the sharing pattern in differential dataflow, an incremental view maintenance platform built on Timely dataflow. Timely is a scale-out data parallel system where all operators are sharded across multiple workers, and each operator instance is in charge of a subset of the input data. In order to make sure operators can access their shard of the index through shared memory, we can make sure to shard the arrangements with the same key as the operators that access them. Now that we have seen how we've built shared arrangements, let's move on to evaluation. Our first experiment is designed to check whether we have accomplished our goal of increasing efficiency of streaming systems, supporting both dimensions of change we mentioned at the start. Data arriving continually to update input relations, and queries being installed and retired by the user. We will check that arrangements improve the latency for deploying new queries and obtaining first results, that they enable low latency maintenance as new data arrives, and that they reduce the memory footprint when many concurrent queries can share the same indices. Our first experiment is based on TPCH. We use a setup in which the 8 relations in TPCH are loaded progressively, one record at a time. We interactively deploy and retire queries while the relations are loading, and we make sure that 10 queries are active concurrently at any time. To evaluate the deployment of new queries, we measure the latency between the time a query is installed and when the initial results is returned. This histogram shows which fraction of the queries installs and starts returning data within a given time frame. Without shared arrangements, most of the queries take almost a second to return results. When we replace private indices with shared arrangements, the majority of queries return a result in less than 10 milliseconds. This is important because it provides an interactive experience to the data analysts who submitted the queries. To assess whether the additional complexity introduced by shared arrangements negatively impacts view maintenance, we measure the latency with which the results are updated in response to new inputs. This plot shows what's the fraction of new inputs for which the system is able to update the results within a certain latency, shown on the x-axis. As you can see, shared arrangements don't slow down incremental view maintenance, and in fact improve responsiveness by roughly a factor of 2. This is due to the fact that shared arrangements eliminate redundant work in maintaining separate indices. The long tail is due to expensive queries containing inequality joins that respond slowly to changes in their inputs. Finally, we want to check that arrangements indeed reduce resource consumption. We do this by plotting the memory consumption of the system running with and without arrangements as new data comes in, and queries are installed and retired. Memory consumption is almost 3 times lower when we use shared arrangements. From these 3 plots, we can conclude that a system with shared arrangements uses significantly fewer resources, returns results more quickly, and updates these results with lower latency. In the paper, we also compare the performance with and without shared arrangements for interactive graph queries such as lookups and shortest paths. Shared arrangements achieve 5 times lower latency and 4 times lower memory use, and the system performance compares favorably with other general-purpose and specialized graph processing systems. We've also run micro-benchmarks to evaluate the design and scaling characteristics of the shared arrangements in isolation. As you can see in the paper, arrangements display robust, strong, and weak scaling, and the throughput scales linearly with the number of workers. The paper also contains results that compare the systems with shared arrangements with other state-of-the-art systems in 3 workload categories. This lets us assess that the performance gains due to shared arrangements aren't confounded by low baseline performance. In the paper, we showed that the system with shared arrangements outperforms many general and specialized systems for data log workloads, program analysis tasks, and batch graph computation. In summary, shared arrangements enable interactive, incrementally maintained queries against streams by sharing sharded index state between operators. By relying on the single producer, multiple consumer sharing pattern, shared arrangements require minimal coordination. We showed how they yield improved performance and resource efficiency for interactive analytics against evolving data. Thanks for listening.